Okay, we will get going today with first an announcement before I start talking chemistry. The latest organization that wants me to announce their meeting is the Pre-Pharmacy Association. I guess pre-pharmacy is not a major anymore, but they still have an association for people that would like to become pharmacists in the future. They have a meeting tomorrow evening. I can't read their font. I think that says STO 100 or SEC 100. This room. They chose an interesting font for this. But anyway, I think it's in this room tomorrow. They welcome representatives from Texas A&M, so whether that influences your decision to go or not, keep that in mind. And I'm going to close this because it's going to slow me down otherwise. All right, let's get into the topic today, which is going to mostly be about the Bohr model. We have a few loose ends to clean up from last time. So if you remember last Wednesday, we did a lot of things that seemed more like physics than chemistry. We're sort of building up into some of the ideas of atomic structure that come from studying the interactions of light and matter. And what we kind of ended with last time was the idea that was starting to evolve in the early 20th century that electromagnetic radiation or light and matter are not necessarily two separate entities. There used to be this clear divide between them, but at the atomic level, a lot of times that divide gets blurred and there really is what we call wave-particle duality. So the last concept we want to introduce related to that is what's called de Broglie wavelength. So the legend goes that de Broglie came up with this when he was a very young graduate student. I think he has one of the shortest PhD theses on record. It was about 2 pages, and it described this equation and this relationship that he came up with. So if you want to first understand where this comes from, you've probably all heard of one of Einstein's greatest contributions, this simple equation E equals mc squared, which sort of introduced the idea that energy can have an effective mass, which was something that people were, that sort of blew everybody's mind at the time. And so if we look at some derivations that can come out of this, what we can find is that for a photon has an effective mass of E divided by c squared. So we just rearrange that equation and find that the mass of a photon is given by E divided by c squared, where c is the speed of light, the speed of in a vacuum in this case. And then if we do a further derivation, remember we learned last time that the energy of a photon is h times c divided by lambda, where h is that new constant, Planck's constant, related, which is important for understanding the energy of a photon, and then lambda being the wavelength. So if we put that back into here, we replace energy with hc over lambda, and then simplify a little bit of algebra, we get h over lambda c. So in other words, the mass of a photon depends only on its wavelength and 2 constants. So h being the constant, Planck's constant, c being the speed of light. So the mass of a photon depends on 2 constants, which means in a more general sense, for anything, we can rearrange this and solve for wavelength. So this form of the equation here says that a photon has an effective mass associated with it, or we can think about things in the opposite way, which is that if you have any particle, any piece of matter, it has an effective wavelength associated with it. Lambda is equal to h divided by, I think I might have left a mass out here somewhere. No. Anyway, we rearrange and we get mv. Sorry, I was confusing myself. So where v is just, in more general sense, the velocity. So for a photon, it moves at the speed of light, so its velocity would be c. In more general sense, v is just any velocity of a particle. And so de Broglie basically came up with the idea that all matter has a wavelength associated with it. Another sort of concept saying that matter has wave-like properties and vice versa. Now you might wonder, why did it take so long for us to recognize this, or is this even true at all? And for regular scale objects, you don't really see this very, very easily. So if you think about the constants that are involved in here, h being the main one, h is an extremely tiny quantity. We saw that it was 6.626 times 10 to the minus 34. So for most regular objects, if you try to calculate the wavelength, it's going to be imperceptibly small. So for example, if I wanted to wake someone up in the back of the room and throw a baseball as hard as I can to the back of the room, assuming I can still throw it that far at my age, the velocity would be somewhere on the order of 90 miles an hour, no, 50 miles an hour, which is 25 meters a second or something. The mass of a baseball is on the order of hundreds of grams. So if you put the mass and velocity of a baseball into that equation, the wavelength is going to come out to, I don't know, probably like 10 to the minus 20th meters or something really stupidly small like that compared to the size of a baseball. So compared to a regular object, its effective wavelength is extremely tiny. You don't even worry about that. But when we're talking about things that are really, really small like electrons, they actually do have a noticeable wavelength compared to the size scale in which they operate, which they are. So when you're talking about really small particles moving very fast like electrons, those are going to have noticeable wave-like properties, and there are some experiments that have been done to demonstrate that. So let's sort of summarize this whole idea of wave-particle duality, where the de Broglie wavelength is kind of the concluding piece of that. So matter and energy both have dual particulate and wave properties, so there is no distinct separation between the two. And it's important to realize that this wave-particle duality only manifests itself in certain situations. We don't see it all the time, which is why in a lot of cases we don't even think about it or don't notice it. But in some situations, this wave-particle duality is important when we're talking about things like photons, and we're talking about very, very tiny particles like electrons. That matters. And so one of those key ideas then is that electrons exhibit wave-like behavior. And so there's a lot of theoretical work that describe that, the de Broglie wavelength being the key one, which is that even if you have an electron, which we typically think of as a particle, it has a defined mass, it has a charge associated with it, it will in many cases behave like a wave. And the experiment that proved this, I'm not going to give a lot of details about this one, but there's this thing called diffraction you may have heard of. Now, diffraction is scattering of light by a regular array of points so this is kind of a classic experiment you do in physics class, where you take a diffraction grating, you shine light through it, and you get spots of constructive interference and then dark spots where there's destructive interference, all that stuff. So that's kind of what you see with diffraction. It's just the scattering of light as it hits one of those regular arrays of points or lines, and as it turns out, electrons are diffracted when you shoot them through a crystal. So you need a very small atomic level spacing to see it for electrons, but if you put electrons through a crystal, which is a regular array of atoms that they can diffract off of, you do see the electron beam being diffracted, much like you would expect an X-ray beam or a light beam to be diffracted in the same way. So this diffraction, all you really need to know about it is that it was the experiment that kind of proved the idea of wave-particle duality that de Broglie had come up with, and showed that these electrons do have a property, diffraction, which was traditionally thought of as being only associated with waves. Alright, so that's sort of the last physics thing. Let's do a few sample problems before we move on to sort of get an idea of the types of more numerical problems we'll have to do on these topics. So most of what's important in this section is just the energy of photons and how we can calculate those in different ways. And so let's look at the first one here. Let's say we have a red laser pointer, and it has a wavelength of 635 nanometers. We want to know what is the energy of a single 635 nanometer photon. So if we were looking for the energy of one photon, there's an equation for that. So E equals h nu. And then we also should realize that, as we saw much earlier, there's a relationship between frequency and wavelength. Lambda times nu equals c. So if you know these two equations, these are really the only two equations you have to know for properties of waves and photons, you can derive a third one, which is often more convenient, which is E equals hc over lambda, the one I gave you in the last slide. So we can rearrange that because we were given the wavelength, so it would be more convenient to use this directly instead of doing two steps. And so then if we want to convert or calculate the energy of the photon, we just need to put in the relevant constants and the given wavelength. So the constants are going to be given to us on the periodic table, and like I said, you'll use them so many times in the upcoming homework assignment that you'll remember them no problem. So this is that h, Planck's constant, again a very small number in terms of its magnitude, and then the speed of light c is 3 times 10 to the 8th. So those are the two constants, and then in the denominator we just need to put lambda. And the part that I've always cautioned you about already is we need to make sure that lambda is in the correct units, because our constants are in SI units, meaning that length lambda has to be in meters, is given to us in nanometers very often, because the sort of the visible light spectrum that we're going to use most often is on the order of hundreds of nanometers. So we need to convert our given wavelength into meters. And this is where I cautioned you last time to make sure you know your prefixes very well, and nano is one we'll use a lot. So if we have a 635 nanometer wavelength and we want to convert that in meters, this is the same conversion we did last time when we were using that other equation. And so 1 meter is 10 to the 9th nanometers, or alternatively 1 nanometer is 10 to the minus 9 meters, however you choose to remember that conversion or use it. It's mathematically the same. And so when we do that, we just divide by 10 to the 9th, we move the exponent over a bunch of times, and we get 6.35 times 10 to the minus 7 meters. And so that's the number that then has to go back up into this equation to get the units to work out right. Alright, so this is why I always emphasize the importance of writing out your units, because if we do that, we can clearly see that our meters cancel out, so those seconds cancel, and all we're left with is an energy in joules, which is the standard energy unit that we're going to use. And so when we multiply those out, we get 3.13 times 10 to the minus 19 joules. Alright, so I think that's the first time we've used that equation to do a real calculation. And we can see, not surprisingly, that a single photon has a very tiny amount of energy. 3 times 10 to the minus 19th is extremely small, but it is a discrete unit of energy that if you had 635 nanometer light, that would be sort of the smallest division of energy you could have in that beam of light. You can't get any smaller than that. That's the energy of one single photon. So that's why we use that equation. We're going to use it a lot today for some other things too, so we'll come back to that and use it some more. Another one that I want to do is somewhat related, but let's say we have a green laser pointer in this case, 520 nanometers is green, and we want to use that green laser pointer to produce 2 joules of energy. So I said in the last problem that a single photon has a very tiny amount of energy, and we want to know how many photons do we need to produce 2 joules of energy if their wavelength is 520 nanometers. So once again, the first thing we're going to do is find the energy of a single photon, because that's what this equation will tell us. And that's really the only equation we have that we can use directly. So we're going to use that hc over lambda to find the energy of a single photon of 520 nanometers. So just again, h times c, and then divided by lambda. Same conversion we did last time, where we have to convert nanometers into meters. I'm not going to show it again, but we take 520 and divide it by 10 to the 9th to get 5.20 times 10 to the minus 7 meters. So a lot of your wavelengths that you're going to be dealing with are going to be on the order of 10 to the minus 7 meters, because as I said, a lot of the wavelengths that we use for visible light are on the order of hundreds of nanometers, which is equivalent to that. So we put that in and we get the energy of one photon in this case is 3.82 times 10 to the minus 19 joules. And again, that's the energy of a single photon, which is an important consideration for this problem especially. So if we compare that to the last one, this is green light. It has a longer wavelength, Roy G. Biv, which means it has a higher energy. Remember, those two are inversely related. Lambda here is in the denominator. So our previous photon had an energy of 3.13 times 10 to the minus 19. This one is 3.82 times 10 to the minus 19. So the answer makes sense compared to the last one. And then finally, but what this one is asking, though, is not for this number. It's asking for how many photons do we need if we want to produce 2 joules. Now we should recognize that each photon has a very tiny amount of energy, so if we're going to produce a full 2 joules of energy, we need a lot of photons. Let's figure out how many that is. And what we're essentially going to do is use that number we just got as a conversion factor. So if we want 2 joules of energy, we know that each photon, one photon, has an energy of 3.82 times 10 to the minus 19. That's the number we calculated. So joules cancel out, and that gives us then the number of photons. So we're just going to divide those two and get 5.23 times 10 to the 18 photons. So a very large number of photons to produce a full 2 joules of energy. Alright, so really the point of this problem was just to emphasize the point that this equation, hc over lambda, which you're going to use over and over again, is the energy of one single photon. It doesn't represent the energy of a whole collection. It's just one single photon has that energy, and this is how we can then use that to figure out how many photons we need for a much larger amount of energy to be produced. Okay, let's just do one more. Again, I encourage you to try these on your own, but I'll go through it now just so you have the work in front of you and can see it. The work function is the minimum energy required to emit an electron from a metal surface. So we talked about the photoelectric effect last time, which is the idea that when photons strike a metal surface, they can eject electrons from that surface. And we said there's what's called a threshold frequency, which is the minimum frequency of light which will eject an electron. And then the corresponding energy that's associated with that frequency is called the work function. So that's really the same concept, just two different ways of defining it, or two different ways of naming it, I guess. If the work function of rhodium, which is one of the metals on the periodic table, if that's 7.98 times 10 to the minus 19 joules, which of these wavelengths of light will eject an electron from rhodium? All right, so what we're talking about the photoelectric effect is, again, the idea that not all wavelengths of light are going to have enough energy to eject an electron. You have to get to that certain threshold energy, which we call the work function. And so we want to figure out which of these wavelengths, 225 nanometers, 325, or 175, have enough energy to be able to eject an electron from the surface. And so what we're going to do is we want the situations where the photon energy is greater than the work function. Right, because the work function represents the energy of a photon that has the bare minimum amount of energy to eject the electron. So any case where the photon energy is greater than that will result in the photoelectric effect, will result in electrons being ejected from the surface. The work function is sometimes abbreviated as E sub 0. So we saw that nu 0 was the threshold frequency. The corresponding energy is E0. And so what we want is that the energy of our photon, which is equal to hc over lambda, has to be greater than E0. Now what we should recognize is that lambda and energy are inversely related, so if the wavelength is going to be if the energy is going to be high enough to eject a photon, that means the wavelength has to be something smaller than whatever the threshold wavelength is. So when we rearrange this equation, what we see is that lambda has to be less than h times c divided by the threshold energy E0. So we're taking this inequality here and just rearranging it. And so when we put the numbers in, 6.626 times 10 to the minus 34 again, 3 times 10 to the 8. And then E0 is the threshold energy, which was given to us in the problem, is 7.98 times 10 to the minus 19 joules, which equals 2.49 times 10 to the minus 7 meters. All of our answers are given in nanometers, so we're going to have to convert that back up by multiplying by 10 to the 9th. That's equivalent to 249 nanometers. So what this inequality tells us is that in order for an electron to be ejected via the photoelectric effect, the wavelength has to be less than 249 nanometers. Right? Because energy and wavelength are inversely related. So if the energy has to be greater than 7.98 times 10 to the minus 19, the wavelength that corresponds to that is 249 nanometers, which means the wavelength has to be smaller than that. So that's a topic that's going to come up a lot, and to make sure we can understand both conceptually and, of course, with the equations that we're using here, the idea that energy and wavelength are inversely related. So if you want to have higher energy, you need to have a smaller wavelength, and vice versa. So for photoelectric effect, we need the energy of the photon to be larger than 7.98 times 10 to the minus 19, which means the wavelength has to be smaller than 249 nanometers. So both of these will work. A and C are smaller than 249 nanometers. So both of those photons, 225 nanometers to 175, would have enough energy to eject an electron from the surface. 325 nanometers, a photon with that wavelength would not have enough energy and nothing would happen when it hits the metal surface. So that's the photoelectric effect, and it combines that concept with using this equation for photon energy and the recognition that energy and wavelength are inversely related. All right, any questions on these topics before we move on to something else? All right, so you'll see a lot of homework problems related to this, I'm sure, so you'll get some practice during the week as well. But let's move on to some things that are going to start to look a little bit more like chemistry now, finally. All right, which is atomic line spectra. So if you've ever played with a prism, you know that white light, the light that comes from the sun or from artificial sources, has a whole rainbow of colors associated with it. And so if you take a continuous spectrum, as we call it, which is white light, it includes all wavelengths of light, and you put it through a prism, you'll see that it includes all of those. So that's what this continuous spectrum refers to. All right, so that's what we mean by a continuous spectrum. It's where all wavelengths of light are present. You get this, sort of a smeared rainbow picture where you can see all the colors all running together and all of them are present. However, when people started studying hydrogen, what they found was something a little bit different. So people were starting to recognize the idea that electrons and photons are related to each other, and they kind of appreciated that, well, if electrons have different energy levels in an atom and they're moving around, they're going to maybe generate light. And once again, the assumption was, well, if any energy level is accessible to the electron, it would give off any color of light. Just basically any value of the wavelength would be possible. But what they found instead was if they charged up a sample of hydrogen, so they either put a really large really large electric current into a sample of hydrogen, and they saw that it was glowing, which showed that it was generating light. And they took that light and they put it through a prism, and instead of seeing a continuous spectrum, they just saw 4 wavelengths: 410, 434, 486, 656. Those are the ones that occur, at least in the visible range that they could see. There are other ones that would be in the ultraviolet, too high energy to see for us. And this is true for a lot of substances as well. So it's not just for hydrogen. When you energize a substance, it gives off light. That's what we mean by an atomic spectrum. But for any element, in this example here showing hydrogen, only a few sharp lines are observed. So you don't see all colors of light coming off of hydrogen or any other element. You just see a few sharp lines, each corresponding to a discrete wavelength. Okay, so that's sort of the observation that people saw with hydrogen and other elements, is they don't give off continuous light, they just give off these discrete wavelengths, and only those ones are ever observed. It doesn't matter how much energy you put into the sample, none of the conditions matter. These are the only 4 wavelengths of light that you will ever see in the visible range from a sample of hydrogen. So that's what the hydrogen line spectrum was, and this was another one of those experiments that initially baffled people who thought that if we have electrons able to access any energy level they want, we shouldn't be restricted to just 4 discrete wavelengths. We should be able to see any color of light coming off of hydrogen. And that wasn't the case. And so the model that was used to explain this observation is called the Bohr model, and that's what we're going to spend the rest of our time on today. So there are basically three key considerations for the Bohr model. There might be more than three depending on how you divide them up, but I'll give you three points here about the Bohr model. The first is that the Bohr model was formulated specifically for the hydrogen atom. We will talk about later on what its limitations are, but for the hydrogen atom, it only has certain energy levels that are available to the electron. Alright, so it's the idea that the electron cannot just be at any random energy level. Only certain ones are available. And what determines these energy levels are fixed circular orbits of the electron around the nucleus. So it was already appreciated at this time that there's this dense nucleus in the center and that the electrons are somehow surrounding that nucleus. And the Bohr model proposes that those electrons move in fixed circular orbits. This is what is often called the planetary model of the atom, the idea that the nucleus being the sun and the electrons being the planets rotating around that sun. So this was one of the earliest pictures of how the electrons are arranged around the nucleus, and it assumed that they have discrete circular orbits, and also that there are only certain radius of orbits that are available. So it's not that it can be any distance away from the nucleus, only certain ones are even allowed by the Bohr model, and that's what gives rise to those discrete energy levels that result in only 4 wavelengths of light being observed. So that's what the Bohr model tells us about the movement or the arrangement of the electrons around the nucleus. And another important point is that the atom's energy does not change while the electron moves in a particular orbit. Now, one of the weaknesses of the Bohr model that we're going to maybe start to appreciate already is that it doesn't really explain why this is. Why are there only certain circular orbits that are allowed, and why doesn't the electron, which is negatively charged, just crash into the positively charged nucleus? But it assumes that these electrons are fixed in these circular orbits, and as long as the electron stays in the same orbit, as long as it doesn't move further away from or closer to the nucleus, as long as it stays in that same orbit, the energy of the atom is going to stay exactly the same. There's no change in that energy. So that's the second point about it, which is about the atom's energy, which is not changing while the electron moves in that orbit. And then finally, the third point is that when electrons do change to another energy level, or another orbit as it's called in this model, so that can happen. It's not to say that it never happens. So when it moves to another energy level or a different orbit, as it is in this terminology, it does so by absorbing or emitting a photon. Okay? So, as point 2 says, if it stays in the same orbit, it's going to have the same energy. If it moves to a different orbit, the energy has to change. And the amount of energy that it either gives off or absorbs in changing to a new energy level is equivalent to the photon that is absorbed or emitted. So the energy of the photon that's involved in these processes is equal to the absolute value of the change in energy of the atom. So the atomic energy is either going to go up or down. We'll see the differences between whether it's increasing or decreasing. And that delta E, anytime you see the Greek letter capital delta, which looks like a triangle, that means final minus initial. So it's whatever energy the atom ends up at minus whatever energy it started at prior to absorbing or emitting that photon. Okay? So that's the relationship between the energy of the photon that's absorbed or emitted and the change in energy for that atom as it absorbs or emits that photon. Okay? So those are the key parameters of the Bohr model. Let's talk about a few more terms and definitions that are associated with this to help us understand this a little bit better. So that we're going to start talking a little bit about quantum numbers. Now we have a much more detailed discussion of quantum numbers coming next time. But in the context of the Bohr model, there are these things called quantum numbers, which are positive integers. So by positive integers, I mean 1, 2, 3, 4, 5, whatever. And they are associated with the radius of an electron's orbit. So we'll see a picture of this on the next slide or so. But it essentially, if you have a quantum number of 1, that's the orbit that's closest to the nucleus. If the quantum number is 2, that means the electron has moved farther away. If it's 3, it's moved farther, and so on. So each of these quantum numbers, 1, 2, 3, and 4, is associated with a particular radius of the electron orbiting the nucleus. And the abbreviation that we use for this quantum number, we'll have other quantum numbers introduced later. For this one that's associated with the Bohr model is n, lowercase n. And as we'll see, the radius and the energy both depend on n. We're not going to give the equation for the radius because that's not particularly meaningful, but we are going to see how the energy of the electron depends on the quantum number n. Okay? Another term that's very important for the Bohr model is what's called the ground state. This is the situation where n equals 1, and this is the lowest energy orbit. Right? As I said, the equation's coming here in a minute, but when n equals 1, you're at the lowest energy level, you're at the orbit that's closest to the nucleus, and that's the lowest energy. And this gives me an opportunity to tell one of my favorite chemistry jokes. So if you have a hamburger and a steak, which one is lower in energy? The hamburger, because it's in a ground state. Okay, so that's one of my favorites. You'll see others, but it's a good one. And now's the opportune time to introduce it. So ground state means lowest energy orbit for an electron around an atom. It also means n equals 1 if you're doing the quantum number. All right, now the other two terms, we saw these words on the last slide. So what do they mean? Absorption and emission. I said that these changes in energy are associated with absorption or emission of a photon. So if you have a photon that interacts with an atom, so the photon strikes the atom and it has the right energy to do this, it's going to, the energy from that photon can get transferred to the atom, and it's going to cause the electron to move to a higher energy orbit. Okay? So that's what we talk about absorption. It's the photon interacting with the atom, and it causes the electron to move to higher energy. And so what this means is whenever you have absorption, the energy of the photon has to equal to the change in energy of the atom. That's still true. So only a photon that has the correct energy will be able to promote this increase in energy of the electron, and those are going to be positive numbers greater than 0. So when you have absorption, the energy level of the atom goes up. The energy from the photon is transferred to the atom, and the energy goes up. And so another way to think about this is that the photon is consumed by the atom. It's a very weird way of putting it, but that's essentially what happens. The photon goes away, gives its energy to the atom, and the atom goes up in energy from there. So that's what we mean by absorption. And then emission is the opposite process. So if you have an electron in a higher energy orbit and it moves back down closer to the nucleus to a lower energy, the energy goes down in this case. So when an electron moves from higher n to lower n, so that means the value of n is decreasing. And when this happens, a photon is generated. And this is why when you put a lot of energy into an element like hydrogen, you see light being generated, because the energy that's put into the atoms causes the electrons to go up higher in energy, and then when those electrons come back down in energy, they generate a photon. And that's where those lines come from in the hydrogen line spectrum. So that's what we mean by emission. It's a generation of a photon. In this case, the energy of the photon is still equal to the absolute value of the change in energy for the atom, but the change in energy for the atom is negative in this case. So when you emit a photon, the electron goes to lower energy, which means that the delta E is negative, less than 0. You cannot have negative photon energies. The energy of the photon that's produced is still a positive number. You can't have a negative photon energy or negative wavelength or anything like that. But the atom itself has a delta E that's negative. Delta E can be positive or negative since it's a change in energy. Alright, so those are some of the terms and concepts associated with it. So let's go ahead and then draw the picture that's associated with the Bohr model. Alright, so we've been talking about these circular orbits, and this is kind of what they look like. Now, as I said, there is an equation that predicts the radius. We're not going to talk about that equation. So they're not, these radii are not to scale. I just drew them as equal concentric circles. That's not physically realistic, but it doesn't really matter for our purposes. And like I said, you have your nucleus in the center. And then each of these orbits around the nucleus corresponds to a different energy level. So you have n equals 1 is the one that's closest to the nucleus. N equals 2, n equals 3, n equals 4, n equals 5, and so on. However many, you can go up to infinity, really. So those are the energy levels arranged around the nucleus. The circular orbits get bigger and bigger as the value of n gets larger. And then we can also draw pictures for the energy levels on a vertical scale. So here we have energy going up. And in this case, I did draw them to scale. And so we'll get the equation here in a minute, as I keep alluding to. But anyway, the lowest energy ground state is n equals 1. And then the higher energy ones have the higher values of n. N equals 2, n equals 3, n equals 4, and n equals 5. As you'll see, and as this diagram correctly depicts, the energy levels get smushed closer and closer together as you go to higher and higher values of n. So there's a relatively large separation between the first two, and then the separation shrinks and shrinks and shrinks and shrinks, such when you get to very high values of n, you have very closely spaced energy levels, almost continuous, as it turns out, but not quite. Alright, and then if we talk about the atomic line spectrum, so we saw that in hydrogen there's 4 wavelengths that are generated. We'll talk about 3 of them on this slide that we can easily see with our naked eyes. And so what those correspond to is the electron moving between different energy levels. So all of the wavelengths of light that we can see from hydrogen correspond to a transition going from some energy level down to n equals 2. So if we have an electron at n equals 5 energy level, the furthest orbit that I've drawn, and that goes down to the n equals 2 level, that's going to generate a photon. And so if we go from n equals 5, oh great, I'm slowing down again. Just my tablet's break time. Okay, so if we go from n equals 5 to n equals 2, that gives us that 434 nanometer photon that we saw was part of the hydrogen line spectrum. And that would appear blue, that's why I drew it in blue. And then if we go from n equals 4 to n equals 2, that's going to be more of a blue-green color, 486 nanometers. And then finally, that one that shows up as red would be n equals 3 to n equals 2. And that's going to be 656 nanometers. Alright, so it's not that other transitions are not allowed in any way. We could have any combination of n values that would emit a photon. So we could go, n equals 5 to n equals 1, n equals 4 to n equals 1. But the ones that occur in other combinations of n values occur in the ultraviolet or the infrared region. These are the 3 that occur in the visible region, and they all terminate at n equals 2. Okay, so that's why we see the different hydrogen lines, the different discrete wavelengths of light that come off of hydrogen, because the electron gets excited to one of these outer orbitals, they can then relax to one of the lower values of n, and that gives these different energy levels. Yeah.
Are there values only for hydrogen atoms?
Yes, those will only be for hydrogen atoms, and we're working very close to the equation now, and you'll see how it depends on the identity of the atom as well. So these ones are for hydrogen. Other atoms would give different wavelengths of light. That it does depend on how many protons are in the nucleus as well. All right, so let's then finally get the equations that I've been teasing you about for the last several minutes. What are the equations that are associated with these? Find my page of notes. Okay, so the first one is the equation for the energy levels themselves. I believe this is a constant you'll have to memorize. I don't think it's given on the periodic table, but it's, again, a very common number that you'll use a lot. So the energy level is minus 2.18 times 10 to the minus 18 joules. That's the constant that goes out in front. And then the two parameters that the energy depends on. So this is the energy level of an electron, a certain distance from the nucleus. It depends on z squared over n squared. Okay? And if we look at this equation, this is they're all defined as negative numbers. The reason for that is it's an attractive interaction between a positive and a negative charge, and by convention, when you have two oppositely charged particles attracted to each other, you define the energy of that interaction as being a negative number. So that's why it's a negative number all the time. And you see that it approaches 0 as n goes to infinity. Okay, so the value, so for the small values of n, you're going to have a more negative number or a larger magnitude of your energy, and then as you go further and further out, the number is going to get closer and closer to 0 asymptotically. Now, what do these two terms here mean, z squared and n squared? So this is where it depends on the identity of the atom, and this is why the question that just came up is very timely. This is the atomic number, the same z that we've defined last time, which is the number of protons in the nucleus. So if you add more protons to the nucleus, that does influence the energy levels. All right, now as far as I know, I haven't looked at all of them in detail yet, and they may have changed. I think all of the homework and test questions deal with the hydrogen atom. So for the hydrogen atom, z equals 1, and basically that term just drops out. But for completeness, I wanted to show you that, yes, it does depend on the number of protons in the nucleus. And if you encountered something other than hydrogen, you would have to include that z squared term in there, which would be, the number of protons, 2 for helium, 3 for lithium, and so on. And then n is still that quantum number that we just finished defining, which is reflective of the radius of orbit. So those are the two terms that the energy levels depend on. Now, the form of the equation we're going to use most often, it is still, of course, possible to use this first equation to calculate the absolute energy level of an electron using the Bohr model, but we often look at changes in energy because we're interested in the processes that result in absorption or emission of a photon. So delta E being E final minus E initial, we put the constants out front, minus 2.18 times 10 to the minus 18 joules, z squared, and then 1 over the final value of n squared minus 1 over the initial value of n squared. Okay, so whenever an electron changes energy levels, whenever there's a delta E, there's going to be two different values of n involved, wherever the electron starts, wherever the electron ends up. And so in this equation, NF is the final n value. That's where the electron finishes, I guess you want to put it that way, where it ends up in the atom. And then Ni is the initial one, where it started. And depending on whether we're talking about absorption or emission, Ni could be smaller than NF, or NF or Ni could be larger than NF. And as long as you put them into this equation in the correct order, then you'll get the correct sign for delta E. So delta E can be positive or negative, and that is determined by whether the final value of n is larger or smaller than the initial value of n. So that all comes out from the math. You don't have to necessarily worry about keeping that straight. All right, so those are the equations for energy levels and delta E. A couple other things we can talk about that are related to this. the ionization of a hydrogen atom. So one reason that the Bohr model was accepted when it first came out is because it correctly predicted the ionization energy of hydrogen. Ionization energy is something we're going to talk about in a lot more detail very soon, but it's the amount of energy that's required to completely remove an electron from the nucleus. So if we want to form an ion, remember an ion is something that has either extra or too few electrons. So if we want to form a positively charged ion, the ionization energy is how much energy it takes to rip that electron away from the atom and form the completely separated positive ion and the electron that goes off into the ether. Okay, so if we're going to talk about the ionization energy, what that means anytime we're calculating ionization energy is that the final value of n goes to infinity. Because this is the situation where the electron is completely removed and it's not going to be bound in a nuclear orbit anymore. So we can then use the Bohr equation to calculate the ionization energy of hydrogen. And so if we're starting with ground state hydrogen, delta E is again this equation here. One over NF squared minus 1 over Ni squared. For ionization, we're starting with our final value of NF is infinity, as we said. And then if we're starting with ground state hydrogen, the initial value of n is 1. And so this term goes to 0. 1 over infinity goes to 0 if you kept up with your pre-calculus studies. And then we get 2.18 times 10 to the minus 18 joules. So this constant that goes out in front of our equation represents the ionization energy of hydrogen, and it is the correct measured value. So the Bohr model is at least consistent with that, so that was one of the reasons why people were happy with it at first, because it does correctly predict the ionization energy of a hydrogen atom, which we can measure using experimental techniques. And then finally, probably the most important concept, which we're going to talk about, is the related wavelength of absorption or emission. All right, so we've already said that the energy of the photon that's generated or absorbed is equal to the absolute value of delta E, which means then the wavelength of the photon that's associated with a change in energy for an atom is going to be equal to hc divided by delta E. All right, so there's going to be a lot of problems in the homework assignments where we'll give some examples here where we say, what is the wavelength of light that's associated with hydrogen going from its ground state to n equals 3, for example. And so what you do is you use the Bohr equation to calculate delta E. So this value here comes from the Bohr equation. And then once you know the change in energy, you know that the photon energy is going to be equivalent to that, and that's going to then you're going to work backwards using the equation for a photon. So a lot of these problems are going to have really two concepts and two equations associated with them. The Bohr equation to determine the change in energy for the electron as it moves between different orbits in the atom, and then you're going to use the equation for photon energy to figure out how that change in energy relates to the photon that's either generated or absorbed. So we'll see some examples of that today. And another thing to keep in mind when you're doing these, and to make sure that your answer makes sense, is especially if you're asked to calculate delta E, you have to get the sign right, because delta E can be positive or negative. And so always remember that a positive delta E corresponds to absorption, and it corresponds to a situation where you're starting with a low value of n and going to a higher value. Right? So if n is going from 1 to 2 or 1 to 3 or 2 to 4, starting with a low value, ending up at a higher value, you should get a positive delta E. If you don't, that means you probably put them in the wrong order. And then similarly, the opposite process, if delta E is negative, that corresponds with emission. And that's a situation where you're starting out in a higher value of n and ending up in a lower value. Right? So if you have that situation, you should calculate a negative delta E. If you don't, it probably means you reversed the initial and final values of n in the equation. So it's always important not just to blindly trust the numbers that your calculator spits out at you, but to make sure that they're reasonable. And at least in these problems, getting the sign of delta E is something that should be conceptually pretty simple to do if you can remember the difference between absorption and emission. All right? Now, the major limitation of the Bohr model, I want to point this out now so it doesn't generate any confusion. We saw that the equation has that z squared term, which is the number of protons in the nucleus. That's the part that is determined by the nucleus for that equation. However, this equation only applies to one electron systems. So you can have different numbers of protons in the nucleus as long as you only have one electron that's surrounding that nucleus. So hydrogen, of course, is the only neutral atom that has a single electron. For other species that work, you'd have to consider, for example, helium plus, which is not a particularly common or stable ion, but one that you could study in the gas phase, I suppose, or lithium 2 plus, beryllium 3 plus, and so on. So it's important to remember that this Bohr equation, this Bohr model, only works for one electron system, so we're going to have to see a more complicated model of the atom coming up soon that applies to multi-electron systems. But for the Bohr model, it really only applies to these special cases. So for, like I said, for neutral atoms, hydrogen is the only one that works for the Bohr model, but there are ions that would work as well. Or if you remove all but one electron, you can still apply the Bohr model to that, accounting for the different numbers of protons in the nucleus. So Z equals 2, 3, and so on. So that's where that Z squared term comes in, but it only works still if there's only one electron that's around that nucleus. Alright, so what we're going to do now are several sample problems associated with the Bohr model to see the types of questions that we can ask you. And there will be others, of course, that you'll have to work out on your own on your homework, but just to get a flavor for some of these. So the first one, true or false? Minus 6.36 times 10 to the minus 19 joules is an allowed energy level for a lithium 2 plus ion. So here we're just talking about a single energy level. We're not talking about an electron moving between energy levels. So we're going to use that first form of the equation that I gave you. The energy level is given by minus 2.18 times 10 to the minus Alright, every time I do this section, of course, I have a panic that I have the Bohr constant wrong, and that should be a minus 19, minus 18. I'm pretty sure it's minus 18. Gosh, I hope so. Every time I look at that, it scares me. I know I've messed that up in the past. Anyway, that's the equation that we're going to use, as long as the constant's correct. I sure hope it is. And so what we need to do for lithium 2 plus is make sure we have the correct value for Z. So in case you don't remember where lithium is on the periodic table, we find it. I think most of you know that lithium is the third element, but in case you forgot, you'll have this in front of you. There's lithium there, atomic number 3. So Z is 3 for lithium, so I think we have to account for that. And so what we're actually solving for here is the value of N. So what we're given the energy, we're given this number here, which is the energy level. We know the value of Z because we know that it's lithium, which has 3 protons. We have to solve for what value of N, what quantum number is associated with that energy level. So it's just a little bit of algebra now. So we put the energy in that we're given, minus 6.36 times 10 to the minus 19 joules. And that's going to equal minus 2.18 times 10 to the minus 18 joules times Z squared, which is 3 squared divided by N squared. We're going to solve for the value of N. So basically we're trying to find what energy level does this, or which quantum number is this associated with. As you'll see sometimes in this course, I'm going to skip over a lot of the algebra details because this isn't a math course. But what we should come up with when we move all the constants over and everything is N squared is equal to 30.85. So basically we just divide both sides, isolate N, solve for N squared. So then N is going to be the square root of that number, which comes out to something like 5.55. So the question is true or false. Is this an allowed energy level? And that leads us to the conclusion that this is false, not a allowed energy level, because remember we said N must be an integer. Alright, and that's where the quantization of energy comes into play with the Bohr model as well. You only have integer values of n that are allowed, 1, 2, 3, 4, 5, 6, which means only certain energy levels are allowed that correspond to those values of n. So this particular energy level that I gave you, if we solve for the value of n, it comes out to a non-integer value, so that cannot be one of the allowed energy levels for lithium. Okay, so any questions on that concept? All right, so then moving on, some other sample problems. We want to determine the energy and wavelength of light emitted when hydrogen jumps from the second orbit to the ground state. So we saw a lot of the wavelengths that are associated with the hydrogen atom when we introduced the line spectrum much earlier today, and we saw that there's 4 that are in the visible region. But let's see what the wavelength is when we go from the second orbit to the ground state. Now, part of this problem is going to be, we only really have one equation to worry about. It's a relatively simple one, but we have to sort of find the unknowns that are that we need. So delta E, in this case we're talking about an electron moving between 2 energy levels, so this is the form of the equation that's going to be relevant to us. Z squared, and then 1 over NF squared minus 1 over NI squared. Alright, so for hydrogen, Z equals 1, so we don't have to worry about the Z term in this case. There's only 1 proton in the nucleus. So that goes to 1. But we need the 2 values of N, NF and NI. So some of the terminology that we're going to start using and being familiar with, second orbit tells us N equals 2, and that's going to be the starting N value, NI. So we're going from N equals 2 to the ground state. Remember that the ground state, we don't explicitly tell you the value of n, but anytime you see the term ground state, you know that the value of n that's associated with that is 1. Okay, so those are the 2 n values we're talking about here. Starting out with n equals 2, it goes to n equals 1, so it's going from a higher energy to a lower energy. It's emitting a photon, and this is the change in energy that's associated with that we're going to calculate first. And so 1 over NF squared, so NF is 1, and then initial N is 2. So 1 over 1 squared minus 1 over 2 squared, we multiply that by the constant, and we get minus 1.64 times 10 to the minus 18 joules. So this is the change in energy for the electron as it goes from the higher value of N to the lower value of N. And now we want to know what is the energy and wavelength of the light. So if we're looking for the energy of the photon, remember that's always going to be given by the absolute value of delta E. Photon energies can never be negative, so we take the absolute value, and the energy of the photon that's emitted has to be exactly equal in magnitude to the change in energy of the atom. Minus 1.64 times 10 to the minus 18 joules. So that's our energy value. We don't even have to do an additional step to get that. We just have to lop off the minus sign because photon energies can never be negative. And then finally, if we want to find the wavelength of that photon, we know that we have an equation for photon energy, E equals hc over lambda, and so we just rearrange and solve for lambda, which is the wavelength. So lambda is equal to hc over the energy of the photon, and now it's just plugging in constants and dividing. Here, everything is already in the correct units. Because the energy of the photon from the Bohr equation is in joules already, so we don't have to convert that or anything. Okay, so those are the numbers we put in. And so what we get is an answer in meters. We get 1.21 times 10 to the 7th meters. We don't specify a unit for this problem, but the more conventional way of recording wavelengths, as I said, is in nanometers. So this would convert to 121 nanometers if you wanted to put it in those units. Okay? So remember that the energy of the photon is always a positive number. So the delta E for the atom is negative, but then the photon energy is always a positive, and same with the wavelength. You can never have a negative wavelength. So when you're doing these types of problems for the Bohr equation, the only parameter that will ever have a negative number associated with it is sometimes the delta E. Delta E can be positive or negative depending on whether, again, the electron is going from higher N to lower N, or lower n to higher n. If you're calculating the energy of the photon, if you're calculating the frequency of the photon, if you're calculating the wavelength of the photon that's associated with that using any of those other equations, those always have to be positive numbers. You can never have a negative photon energy or a negative wavelength or frequency. All right, so that's another good way to check your answers. Make sure that they're at least reasonable, the correct sign. So what does this number tell us? 121 nanometers. So we should keep in mind that the visible spectrum, the spectrum of light that we can see, goes from about 400 to 700 nanometers. So this would be ultraviolet radiation. It's a lower wavelength or a higher energy than the violet radiation that we can see. So this would be a process that certainly can happen in hydrogen. It's not that this n equals 2 to n equals 1 transition doesn't occur when we excite hydrogen, but we just can't see it with our eyes because it produces a photon that's outside of the visible spectrum that we can actually see. All right, so that's what we get for the n equals 2 to n equals 1 transition. Now let's determine a very similar problem, but with energy and wavelength of light when we have lithium 2 plus going from the second orbit to the ground state. So things are very similar in this problem. The only difference here, if we go back up to the equation is that we have to account for the value of Z here, because lithium 2 plus Z equals 3. We've already seen the example with that one. So you just have to remember to put that into the equation. Otherwise, the process is exactly the same. You calculate delta E first. Same constant that goes out in front. But now we have to account for the value of Z, the number of protons in the nucleus being 3 instead of 1. So that's going to change the value that we get. Same two values of n, second orbit, so n final is 2. Sorry, n final is 1, looking backwards. And so same values of n. And so this time we get minus 1.47 times 10 to the minus 17 joules. Okay, so bigger by about an order of magnitude just by changing the number of protons in the nucleus. And so when we calculate the energy of the photon and the wavelength for that, again, that's a negative number because the electron is going to a lower energy level. But the energy of the photon has to be the absolute value of that, always a positive number. So we get 1.47 times 10 to the minus 17 joules for the energy of a photon. And then we calculate lambda the same way. Hc divided by the photon energy. And I won't write out anything here. H and C always have the same definition. They're constants. We put in the energy that we calculated from the Bohr equation. 1.35 times 10 to the minus 8 meters in this case, which comes out to 13.5 nanometers, so even further into the ultraviolet. So these last two show us that if we change the number of protons in the nucleus, it does have a large effect on the wavelengths of the photons that are absorbed or emitted. In this case, it goes from 121 nanometers down to 13.5. All right. Now, another point about the question that came up on the last one, these problems can be a little bit forgiving in terms of the sign, because, as I said, the only time that the sign matters is for delta E. If you were asked to calculate something about the photon, again, the energy, wavelength, frequency, those are always positive numbers, and if you switch the values of n in this equation, you'll still get the same final answer. The only thing that's changed is going to be the sign of delta E, which, if you're asked for that, you need to make sure you have that correct. So, long story short, if you're calculating delta E, it behooves you to make sure that the values of n are written in the correct order. If you're calculating the energy of the photon or the wavelength of the frequency, if you flip the values of n, it's not going to matter in the end because you should always get a positive number for those, and it'll be the same number either way. Okay? But it's best to just get in the habit of doing it correctly, obviously, from the beginning. All right, what else do we have? All right, so here's just a slightly backwards version of this. So the Photon series. So a lot of these atomic line series got named after people, which was, it's kind of done. They didn't really discover anything. They just characterized something and got it named after themselves. But that's how science works sometimes. So the Photon series involves atomic transitions that terminate at the third energy level. So what this means is in a hydrogen atom or in anything that has one electron, it's an emission that involves the final value of n equals 3. And so you see these different lines that are associated with that. A Photon line for lithium-2 plus is observed at 1424 angstroms. Determine the level from which the transition originated. So because it's Photon series, we know that the final value of n equals 3. We're asked to determine what is the initial value of n. Okay? And so that's what we're solving for here. The initial value of n, that when it goes from that value down to n equals 3, it emits a photon that has 1424 angstrom wavelength. Now, one of the reasons that I brought this up is to make sure we understand what an angstrom is, because this is another unit of measure we'll see. So it has this funny symbol in A with a circle above it. And it's just a little bit smaller than an nanometer, 10 to the minus 10 meters. Okay? So it's a little bit smaller than a nanometer. One of the reasons that angstroms is a popular unit of measure in chemistry is because we'll see this a little bit later on in terms of the radius, of, the atomic radius of different species. They tend to be on the order of angstroms. So, for example, a carbon atom has a radius of about 0.8 angstrom. So it's a convenient unit of measure when we're talking about the spacings of atoms and molecules and things like that. So that's why we use it. It's not as commonly used for wavelengths, but here it is. And so we have a 1424 angstrom wavelength. And so the first thing we want to do is convert that into meters, because all of the equations involve standard SI units. So let's just convert this to units the right units right away. So we're just going to divide by 10 to the 10th. Similar to nanometers, it's just one order of magnitude different. And so this 1424 angstroms corresponds to 1.424 times 10 to the minus 7 meters. All right, so that's the wavelength of this photon. That's sort of our starting point. And here we're just going to work backwards from what we did before. So in the previous problems, we were solving for the wavelength of the photon. Now we're given the wavelength of the photon, and we're just going to work backwards to find the associated energy, the energy level changes. All right, so the delta E, or I guess the absolute value of delta E more precisely, is given by hc over lambda. So once we know the wavelength of the photon, which is given to us in this problem, we can calculate the energy of the photon, which correlates with the delta E for the atom as it undergoes that transition. So we plug the numbers in. Same constants we've been beating like a dead horse today. 3 times 10 to the 8th meters per second. And then we divide that by the given wavelength, which has to be in meters for this equation to work, as we've seen. So working it out to about 3 significant figures, which should be more than enough, we get 1.40 times 10 to the minus 18 joules. Okay, so that's the energy of the photon that's associated with this process. And then from here, we have to work backwards and use the Bohr equation to solve for this final value of n. This is where the signs do become a little bit important, because we're talking about, in this case, emission. We're told directly that these are atomic emissions. And so remember, when we're talking about an emission, that means the delta E from the Bohr equation has to be a negative number. So that means the delta E is going to be the negative of this, minus 1.40 times 10 to the minus 18 joules. So if the photon that's produced or emitted has an energy of 1.40 times 10 to the minus 18 joules, the delta E when the photon is emitted is going to be the negative of that. Delta E's are always negative for emissions. And then so we plug this into the Bohr equation. That's the delta E. That's going to be equal to the Bohr constant times Z squared. This is still lithium-2 plus. We have to account for the value of Z being 3. And then the two values of N. The final value of N for a Photon series, as we said, is 3. So 1 over 3 squared is going to go there. It's N final minus N initial. And then we're solving for the initial value of N. So we work out some algebra. We put everything into the magic algebra machine, which unfortunately you won't have access to on your exams. So make sure you can do this yourself. It's a little bit tricky algebra, not too terrible. And so what we end up with is the initial value of n squared is 25. which means the initial value of n, when we take the square root, comes out to 5. And if you did this right, you should get two things to check your answer to make sure it's right. First of all, it should be an integer, because only integer values of n are allowed. If you got 4.34 or 6.78, that means you did something wrong algebraically or numerically. And then the other thing to keep in mind is that because it's emission, our initial value of n has to be bigger than the final value. The final value of n is 3, so that means whatever value of n we solve for here should be something larger than 3 if we're talking about emission. It's always good to check how reasonable your answer is. All right, and then finally the last one, which requires a higher energy photon, moving from n equals 1 to n equals 3 in hydrogen, or n equals 2 to n equals 4 in helium plus. So again, this one is just straightforward application of the Bohr equation. We don't even have to think about this too much. We just have to do the equation twice. So for hydrogen, delta E. Now an important thing to remember too, as we start this problem, is that the energy level spacings are not equal. So even if you're talking about the same atom, even if it's just hydrogen, the spacing between n equals 1 and n equals 3, which is a difference of two values of n, is not going to be the same as the spacing from n equals 2 to n equals 4. So we never want to make that assumption, even if we're talking about the same atom. Here we're talking about two different atoms, hydrogen and helium, so there's more to it than just that. But the energy level spacings are not equal as you go up, so we have to make sure we keep that in mind conceptually for some of the problems we're doing. But here we're just going to plug in the numbers to the equation and figure out which one's bigger. So for the hydrogen, z equals 1, so we just have a 1 out front, and then we put the two values of n in, 3 squared minus 1 over 1 squared, going from n equals 1 to n equals 3. And so this we get 1.94 times 10 to the minus 18 joules. So that's the delta E for hydrogen, and then for helium, oh, come on, really? Almost there. All right, helium. Nope, not yet. Alright, well this is getting frustrating, and one thing I want to do since we have about 5 minutes left is do our first bonus quiz. So I promised that these would come at irregular intervals, so here's the first one. So as I said, you have to do this on one of the bonus quiz forms that's available on Blackboard, so hopefully you came prepared or have a friendly neighbor sitting next to you that can lend you one. This always induces a mild freakout, so let's try to quiet down a little bit so I can relay the instructions. Okay, let's listen up for the important instructions. Now all you need to write on the form is your name, your student ID number, and the answer. I don't need anything else. I don't check your work or anything like that. All I care about is the answer. Like I said, you get 1 point if you turn anything in, and you get 2 points if you have the correct answer. So there's no harm in trying. I hope all of you have the ability to try this at least if you have a bonus quiz form. Now the last thing we need to figure out, we're going to do this a little bit by trial and error today, what's the best way logistically to collect, well, I don't know how many of you are here today, let's say 460 quizzes if everybody's here today. What I want to try to do, this might not work very well, but I think it's going to be a good strategy, is I would prefer if everybody would remain in their seats until you're done so that you're not making a ton of noise and tripping over people while they're trying to finish their quiz. So please be polite to your neighbors. It's only going to be a 1.5 or 2 minute quiz, so it's not going to kill you to sit there. And then once I call the time, once I say that you're done, everybody pass your quiz to the aisle. So these two sections I want you to pass to my aisle here, and then the section on the far right, my far right, pass it to the middle aisle that's closer to the center. And then whoever happens to have the aisle seat, you're the lucky person that gets to bring them to the front, so that I don't have to scamper around the room trying to make sure I collect all of them. So on your way out, if you're the aisle person, just drop the quizzes here. Remember, you're not competing with each other, so don't sabotage your neighbors even if you don't like them. Please turn in their quiz. I'm trusting you guys on this one. And I think that'll be the best way, so I don't have 460 people storming me at the end, and so I don't have to run around the room like a madman making sure I get all of them. So that's what we're going to try. If I have to adjust the collection strategy, I will. I'm going to hate myself tomorrow when I grade these, but that's a problem for tomorrow, not today. So I'll stop the video because we don't need to record this part of it.